Hello, this is the second part of the set theory. In this part, I will be discussing some points, okay, and some examples. The universal set. What is the universal set? A universal set is a set which includes all possible elements with reference to a particular discussion. Universal set is the superset of all these sets. Look at this example. Look at this example. Let A is a set, okay, all Indian males, and B is another set, all Indian females. So the universal set in this case is that means all Indians. So all Indians covers the whole India. So this is the universal set. So what I have mentioned that a universal set is a set which includes all the possible elements with reference to particular discussion. Here the particular discussion is the male and female, in the number of male and female in the country of India. This is the particular discussion. So a universal set is a set which includes all possible elements. So all possible elements, all the Indian, all the males, all the females Indians are, all the male and female Indians are the are the are in the universal set. So this is the universal set. Now the null set. What is the null set? The null set or the empty set. It is empty set. Null means here empty. Is a set of no elements. There is no elements. Must remember, there is no elements. It is generally denoted by phi, by this symbol, okay? Phi. The null set does not bear exactly the opposite sense to universal set. It should be considered here. You do not think that the null set is the opposite of the universal set. It is not the opposite of the universal set, because null set means there is no element in the set. If you consider our previous example, that opposite of the set of the universal set, that is S prime, all non-Indians. All non-Indians. In this example, the universal set is all Indians. The opposite of the universal is all non-Indians. So it does not mean no elements are there, but a set of non-Indians includes persons other than Indians, and it is in no sense a null set. So it can be concluded that null set is not opposite in meaning to universal set. Actually, the null set is the subset of all sets. Because it has no element, so it is a subset of all sets, and it is unique. It should be noted that way, okay? It's not a null set since it has no elements, which is zero. Here you can find zero. Here you can find zero. So zero is element, so it is not a null set. If a null set has zero, then it is not a null set. It is a set. Null set has no element. Now, finite and infinite sets. Sets with finite number of elements are called finite sets, and sets with infinite numbers of elements are called infinite sets. Look, look at this example. Finite set A 2, 4, 6. It has 3 elements. So it is a finite set. But look at the set B 2, 4, 6, 8, dot, infinite. So it is an infinite set. Now, the denumerable set. Set Sets said to be denumerable countable. It means a countable set. When their elements can be counted one by one as 1, 2, 3, it can be counted one by one. So this is the countable set. So look, A1 x such that, this is the symbol of such that x is a prime number below 10. So A1 is a finite set and it is denumerable. You can count it. It is a prime number and you can count it below 10. And A2, x is such that x is a prime number. X is a prime number. So A2 is an infinite set and it is denumerable. X is a prime number. It has no end. It is infinite, but it is countable. So A2 is an infinite set and it is denumerable. Now A3, look at this, x is such that x is a real number. So A3 is an infinite set and it is non-denumerable because it is a real number. It is a real number. So it cannot be counted. So A3 is not a denumerable set. Now here is some operations of set. So look, this is an example. A is a set, A 2, 3. B is another set, 3, 4, 5. So A union B, this symbol represents the union. A union B means 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we just omit the repeated number. Repeated number is 3. So there is 2, 3. Here is 1, 3, 1, 3. We consider only 1, 3. We do not repeat the number. Okay, we do not repeat the number. So now look at this. A is a set A, B, C, D. B is a set C, D, E, F. So A, it means intersection. Intersection means what is common in between the two sets. So C and D is the common. C and D is the common. A, B belong to A set only, and E and F belong to B set only. So A intersection B is C, D. Now this is another example. Look, P is a set, and here X such that X greater than equal to 10. The value of X is 10 or greater than 10. And Q is such that Q is a set where X is such that X less than equal to, it is X is equal to 10 or less than 10. So P intersection Q, what is common in between the two sets? Just 10, because it starts from 10, 11, 12, and here X starts from 10 below 10, 9, 10, 9. So 10 is common in both the sets. So P intersection Q is 10. Here 10 is the common to both P and Q set. Now X all inferior goods. X is a set that represents all inferior goods, and Y represents all given goods. So X minus Y, all goods that are inferior but not given. Okay, all goods that are inferior but not given. Not given good. You should consider this is the x minus a. Now using the Venn diagram, look at this. A, now look, this is the A union B. With the Venn diagram, you can say this A union B, all the elements within this region. If there is some elements is there may be elements here, here also elements. So it is A union B Venn diagram. And this is the A intersection B. So only the common part of both the sets A and B. Now A and B, A minus B is this part. This is the A set and this is B set, and this is only A minus B. This part represents by A minus B. Okay, this is the Venn diagram of A union B, A intersection B, and A minus B. Now some laws of set operation. Law of inclusion. Law of inclusion. This is the law of inclusion. A set A union set A equal to A. This is the law of inclusion. Set of A intersection set of A equal to A. It is also the law of inclusion. Now, commutative law. A union B equal to B union A. Okay. A intersection B equal to B intersection A. This is the associative law. A union B union C, A union with the B union C. Okay. A intersection B with intersection C, A intersection with B intersection C. Look at this example, associative law. Associative law. So it will be very clear with an example. Suppose, look, A is a set of 0 element, and B is a set 1, 2, and C is a set 3, 4, 5. So now A union B union C. So A union B is 0, 1, 2, 0, 1, 2, and C is 3, 4, 5, 3, 4, 5. So ultimately, this set union with this set, we get the elements 0, 1, 2, 3, 4, 5. Okay, 0, 1, 2, 3. And the same way, look at this A union B with B union C, 0 union 1, 2, 3, 4, 5, B union C. So B union C is B union C is 1, 2, 3, 4, 5. So B union C 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So ultimately A union with B union C is 0, 1, 2, 3, 4, 5. So thus the first law is verified. So look at this is this part is equal to this part. Okay, with this example it is proved. Now this is the distributive law. Now the distributive laws. A union with B intersection C, A union B intersection A union C, and A intersection B union A intersection C. Example, for example, you can say, we can prove it by using this example. A is a set, that's element 1, 2, 3, and B is a set 2, 3, 4, and C is a set 3, 4, 5. So A union B intersection C is that 1, 2, 3, because A is 1, 2, 3, and B and C there is intersection, just common element 3 and 4, 3 and 4, so 3 and 4. Now union 1, 2, 3, 4. And this look at the right hand side, there is this part A union B, that is A 1, 2, 3, B 2, 3, 4, so 1, 2, 3, 4, 1, 2, 3, 4, and A union C, the common part in between the two sets. So so you can find the 1, 2, 3, and ultimately 1, 2, 3, 4. So the first part is verified. Now the laws of identity. The laws of identity. Okay. So A union null set is equal to A set. A intersection universal set is A set. A union universal set is S set. And A intersection null set is a null set. This is the loss of identity. Example, you can find the example. Let S is a universal set of vowels in English alphabet, and let A be the subset of S. Okay. Now S is the vowel, is a universal set that has the element of A, E, I, O, U, all the vowels, and A is a subset of these A, O, and null set. No element is there. So A union null set is A, O. Okay, A. It's clear. So now A union universal set. So A, E, I, O, U is a universal set, and now A intersection universal set is A, O, that is A. A intersection null set, that is null set. So proved. Now complement laws. Complement laws. Now A union A complementary complement of A set is a universal set, and A intersection complement of A is a null set. Look at this with this example Venn diagram. You can find this A union complement of A. So complement of A is this is the A set, and its complement is this area. Okay, except this circle, this area is the complement of A. So A union is a universal set. So so this A with union A complement. So this is the whole set. So universal set. This is complement laws. And A intersection A complement, A intersection A complement. There is no element. Okay, there is no element. This set and this set. If we intersect of this, if we like to find out the common element of these two sets, the set A and set complement of A set, there is no element. So now the Demorgans law. Look at this. Demorgans law is the A union B, its complement C intersection complement B, and A union A intersection B complement A complement union B complement. With an example, I try to clear this concept. Okay, I try to clear this concept. Look, let universal set S be the set of all single-digit positive integers, and A and B are assumed to be two subsets of S such that A has elements x such as the value of x is the single digit even positive integer, and B has elements that is the single digit odd positive integer. So let us now test this law. What is the De Morgan's law? Let us now prove this. In this example, AC equal to B, complement of A equal to B, complement of A equal to B, and complement of B is equal to A. Consider now left hand side and right hand side of the first part. Left hand side. A union B and its complement. A union A complement, and that complement is a complement of universal set, that is null set. And right hand side, A complement intersection with B complement equal to A complement intersection with A set equal to null set. So left hand side and right hand side is equal. Left hand side and right hand side is equal. This part is equal to this part. We have proved with the null. Okay. So similarly, we can prove this. Similarly, we can prove this part, left hand side and right hand side also. On the basis of this example, okay, you can understand it very well. This is the De Morgan's Demorgans law. Now, domain and range. What is the domain and range? Let X is the set and Y is another set. The condition is Y equal to 2X. Y equal to 2X. This is the condition. So, R represents the relation between X and Y. So, 1, 2, 1, 2. If suppose X is 1, then Y is 2. If X is 2, then Y is 4. If X is 3, then Y is 6. If X is 4, then Y is 8. On the basis of this relation, we get this point. Okay, here R represents the relation. And X and Y take only some particular values in describing a particular relation. X and Y take some particular values to fulfill this relation. So, in this example, X can take 9 values 1 to 9. In describing the set R, that is the relation, however, varies only over 4 values. Only 4 values 1, 2, 3, 4. It has 9 values, but only 4 values are there, are using to satisfy this relation. Okay, the set of values over which X can vary is called the domain. The set of values over which X can value is called the domain. Domain of the relation. So domain of the relation here is 1, 2, 3, 4. On the other hand, the set of values over which Y can vary in describing the particular relation is called the range of the relation. So range is 2, 4, 6, 8. 2, 4, 6, 8. And 1, 2, 3, 4 is the domain. Now the convex set. What is the convex set? A convex set is a point set. You must remember. Convex set is a point set. And point sets are sets whose elements are points. Whose elements are points, that is the convex set. If the set contains m points, number of 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, and n, a1, a2, a3, a4, dot, 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 am, the m points, then the point set is given by in this way. Okay, the points, all the elements are point. The segment joining this, the line segment joining these 2 points is called the convex combination of the 2 points. The line segment just joining this. So mathematically, the convex combination is given by A equal to gamma A1 plus 1 minus gamma A2, where the value of gamma is equal to 0 or greater than 0 and it's less than 1 or equal to 1. So a point set is said to be a convex set if the convex combination of any 2 points of the set is in the set. Okay, the convex one, look at this. A, B are convex sets, but C is not the convex set. A is A, this is a set, and any 2 points from here to here, if we join with a line, then it is within the set. So it is a convex set. And in the same way, in the B set, the 2 points joining the line, is within the set. So it is a convex set. But here is a point and here is a point. If we join these 2 points, then and some part of the line is out of the set. So it is not a convex set. So this is the condition, and here it is not fulfilled. But in these 2 cases, it is fulfilled. So if a convex combination of any 2 points of the set is in the set, then it is a convex set. Now, Prove that, here is the example, prove that x is a 2 point x and y and such that x plus y less than or equal to 5 is a convex set. We have to prove it. Okay, we have to prove it. X equal to xy and such that x plus 2y less than or equal to 5. Now look at the solution. Let x1 and ay1 and x2 and y2 are 2 points. Are 2 points, okay, of the set X. Then x1 plus 2y1 less than or equal to 5, because x plus 2y less than or equal to 5. So x1 plus 2y1 equal to 5. Just putting the value of this in this equation. And in the same way, x2 plus 2y2 less than or equal to 5. Now the convex combination of these 2 points is given by, as I have mentioned that convex combination is this. Okay, this is the convex combination. So look, gamma x1 plus 1 by 1 minus gamma x2 is the convex combination. And look at this here, a1, so gamma multiplies with a1 and 1 minus gamma multiplies with a2. Okay, this is the a1 point, this is the a2 point. Okay, so a1 x1, here x1, and 1 minus gamma x2 x2. Okay, this is a2, this is a1. The same way you can find that y1 gamma y1 plus 1 minus gamma a2, where the value of gamma is less than greater than equal to 0 and less than equal to 1. So now we gamma x1 plus 1 minus gamma x2 plus 2 gamma y1 plus 1 minus gamma y2, just this relationship. Okay, we put the x1 plus 2 y1, so 2 is there, we add this. Okay, we add this, so equal to, you can find, just simplify it, take out the gamma as a common factor. So x1 plus 2y1 plus 1 minus gamma, take as a common factor, so we have it this. So x1 plus 2y1, we have a value that is the 5. Okay, and x2 plus 2y2 is also the same value 5, because this is equal to 5 or less than, so 5. So 5 gamma 5 and 1 minus gamma 5. So ultimately, with a simple calculation, we get 5 less than equal to 5. So this means that a convex combination of x1 and y1 and x2 and y2 is also a point of the set. Thus, the set is a convex set. So here is the question or problem is that whether the set is a convex set is not, we can prove it. Okay, we can prove it in this way. In this way, we can prove it. Now there is another example. That is the that is used in economics. That is the budget set of consumer is a convex set. We have to prove that the budget set of a consumer is a convex set. Let budget set is given as such that. In this way, the budget is given. So xy is given in such a way that pxx plus pyy less than equal to m. So px the price of commodity x, and py is the price of commodity y, and x is the amount quantity of x of the product. X represents the quantity of commodity x, and y represents the quantity of commodity y, and m represents the money. So this is the budget equation. This is the budget equation, and we have to prove that the budget set of a consumer is a convex set. So if you take any 2 points in the same way, in the previous example, you can find this 2 points x1, y1, x2, y2 lie in the budget set, and take a convex combination of them. The convex combination also belongs to a set. Okay, so since x1, y1, x2, y2 are 2 points of the set S, so this is the situation. Px x1 plus py y1 less than equal to m, and px x2 plus py y2 less than equal to m. The convex combination of x1 y1 x2 y2, that is the 2 point here, it is a1, it is a2. Now on the basis of the condition gamma x1 plus 1 minus gamma x2 and gamma y1 plus 1 minus gamma y2. Now this is the situation px x1 plus py y1. So px x1 x1, so x1 px gamma x1 px gamma x1 plus 1 minus gamma x2 plus 1 minus gamma x2, and again py gamma y1 plus 1 minus gamma y2 as the convex combination. As the convex combination, you can find it in the same way the previous example. Okay, so now gamma we take out as a common factor gamma. So px x1 plus py y1, and we take out 1 minus gamma as a common factor. So px x2 plus py y2. So this value is given m, it is m. So m, this value is also given, this is m. So after simple steps, we get less than equal to m. So this shows that the convex combination of 2 points x1, y1, x2, y2 is also a point of the set. Is also a point of the set because it's less than m. So hence the Badet set is a convex set. I hope you you have got the understanding of these two examples. This is a very important example. Okay. Now there is another problem. In an examination, 20% students passed in economics, 40% students in mathematics, and 15% students in both economics and mathematics. How many students passed in none? কত ছাত্র? How many students passed in none? Use Venn diagram for your answer. Using the Venn diagram, we have to find out the how many students are there who did not pass their examination. So look, in an examination, 20% student passed in economics. 20% student passed in economics. So this is the Venn diagram. Look, this is the Venn diagram, mathematics, economics, and this is the mathematics. Look, so 20% student passed in economics. This is the 20%. This whole is the 20%, and 40% is mathematics. So this whole is the 40%. So there is a common students who passed both the economics and mathematics, that is 15% as given. So this portion is the intersection portion. Both elements are considered in this intersection point. So this is the 15% element. So 15% is there. So what remains is in this part just 5%, because the whole part is 20%. We subtract 15% from 20%, get 5%. So this person is this area is the 5%. So only 5% students have passed economics. From this diagram, it is clear. And only this is the whole portion is the 40%, and intersection that is both economics and mathematics are considered here. So only 25%, just subtracting the 15% from the 40%, we get the 25%. So only only 25% students passed in mathematics. Okay, so we have to find out the how many students passed in none, neither economics nor mathematics. So look, so look, as mentioned in our problem that economics union mathematics, that is E plus M minus E intersection M mathematics. So E union M, that is economics and mathematics, that is 20 plus 40% minus intersection is this person 15%, so 45. So E and M union of economics and mathematics is 45. Okay, is 45. This means that 45% students passed either in economics or in mathematics or in both. Okay, or in both. So what remains? 100% minus 45% equal to 55%. Passed none. Passed none. So if you consider 25, here is the 15%. If you consider, so if you consider or have a closer look in this Venn diagram, then you can find very easily that in economics, only in economics, there is 5% student who have passed, and in only in mathematics there is 25% student. This area, okay, this area, and this area only the economics. So and this area is the intersection, that is both economics and mathematics students are here. So the students who have passed in economics, who have passed in mathematics, and who have passed in both subjects are 5% plus 15% plus 25%, that is equal to 45%. So the remaining part, that is the 100% minus 45%, is the 55%. These 55% students actually passed in none. Actually passed in none. Okay. So I hope in this lecture I try to clarify some concepts of set, and I hope that you have enjoyed this lecture.